Good morning, everyone. Today my topic is distributed profitable deployment of network services to geo-distributed edge systems. My name is Li-Hsing from National Jiaotong University, Taiwan. Here is the outline of my presentation. First, I will introduce NFV, SFC, and MEC. Then I will present our system model and problem definition. Then the proposed mechanisms and simulation results. Finally, the conclusions. NFV, Network Function Virtualization, is a technique that consolidates network functions onto industry standard servers, switches, and storage hardware. This is done by utilizing virtualization technologies. VNF is a software instance that realizes network function. So basically, we convert a hardware-based network function into software-based VNFs. VNFs should be placed on network function virtualization infrastructure, or NFVI. Service function chaining, or SFC, dynamically chains VNFs in some order to provide specific NFV-based network services to users. It's a promising use case of NFV. In this example, from source to destination, we have 5 VNFs that are chained together in some order. Service chain embedding is to deploy a service chain on a NFVI. There are a lot of the issues here, like VNF placement and service function chaining, and also service function scheduling. Conventionally, we place service function chain in a data center, so the embedding of a service chain to data center is of main concern in this research field. Here is an example of service chain embedding in data center. Edge computing is the technology that provides storage and computational resources close to end users. Here we have a lot of MEC servers. They are placed beside wireless access point or base station. These MEC servers are owned by an edge service provider. And in this paper, we assume edge computing servers as an NFVI for service chain. We assume multiple edge systems. Here we have edge service providers. Each provider has one MEC server in each area. We also assume multiple service chains. So the problem is how to deploy these service chains into these edge systems. At first, let's focus on the SFC placement within a single MEC system. Here we have a service chain that consists of 4 VNFs. The service chain has a latency constraint, and for each VNF, it may have a location constraint. Like this one, VNF1 could be placed in a server in area 2 or 3. For this service chain, a possible placement may be something like this. Here we place VNF1 in a server in area 2, and we place VNF2 in a server in area 3. So it looks like this. It's also possible to place VNF1 and 2 in the same area 3, like this. There are other possible placements. Different placements may have different costs and latencies. Some placements do not meet the latency constraint, so we just remove this. For the rest, we should pick up the one that has the minimal cost. Now we consider the service chain placement to multiple edge systems. Here, if service chain 1 is to be served by the first edge service provider, then for this service provider, the best placement may be something like this. But if the same service chain is to be served by the second service provider, then for this service provider, the best placement may be something like this one. Remember, we may have more than 2 service providers. We may have the third one and also others. Also, we may have more than 1 service chains. We may check the possibility of every network service deployed in every edge system. For example, here is when network service 1 deployed in the second edge system. The cost will be this, and the latency will be theta2, and the payment is P to1. We consider it as a matching between the first network service and the second edge system. Okay. For this matching, the network service provider's utility is his budget. Okay. Network service provider 1 has a budget for this deployment minus his actual payment. So it's the amount of money saved by this matching divided by the resulting latency. For the edge system, his utility is simply his profit. That will be the income minus the cost. Problem formulation. Network service providers and edge service providers have different objectives. Here, they have to decide the value of this indicator variable xik. Xik is 1, means network service 1 is served by edge system k. They also have to determine the payment when network service I is indeed served by edge system k. The indicator variable should be either 0 or 1, and this means the network service can only be served by at most 1 edge system. And these objectives are subject to some constraints. For example, every VNF should be served by exactly 1 server. And we have a location constraint for each VNF. We have a capacity constraint for each MEC server. And we have latency constraint for the service chain. Finally, we have a budget constraint for each network service. We proposed a 2-layer match mechanism for this problem. First, network service provider asks edge systems for possible deployment of their network services into these edge systems. Each edge system attempts to deploy the service chain by matching VNFs in the chain with their servers. Then they report back the resulting latency and the minimum asking price for this deployment. Okay. The minimum asking price has something to do with the cost of this deployment. Then bargaining between network service providers and edge service providers are conducted. Finally, the result is a match between network services and edge systems. The bargaining process is between network service providers and edge service providers. Each network service provider has a preference list that is based on his utility. For example, NSP1 prefers ESP2 the most because the possible deployment in ESP2 will give NSP1 the highest utility. So every network service provider sends his offer with the bid price to the most preferred ESP. A ESP may accept the offer if the ESP has enough resource. Otherwise, the ESP may have to reject less preferred offer. The rejection is based on this value. The bid price offered by network service provider divided by the weighted sum of the amount of resource demanded. In this example, ESP-M rejects NSP-N but accepts NSP-2. Note that the acceptance is only tentative. If edge system K rejects network service provider I, network service provider I may raise his bid price by adding delta to it. Network service provider I may submit a new offer with the new bid price to the same edge system K. If this new offer is still the most preferred one, that means the utility even after the addition of the delta is still the highest among all. If this is not the case, then network service provider I may submit his offer to another edge system provider. Network service provider I stops bidding when his offer is finally accepted. Edge service provider may reject a tentatively accepted offer when he later receives a better offer. That is, when the new offer has a high bid price divided by the weighted resource demanded, then some old ones. And also the edge service provider cannot serve the new network service unless he rejects some tentatively accepted old offer. Therefore, the acceptance of the edge service provider is only tentative. However, the rejections are final. So we call this the deferred acceptance algorithm, DA. It's a well-known algorithm in matching. Because we have money involved, so it's DA with transfer. Then another issue is about server allocation. Okay. Instead of exhaustive search, we allocate servers to VNFs based on the same idea as DA. Okay. So we match VNFs in a service chain with servers. Here we have 4 VNF. Then we have a lot of servers, and we try to match VNF with server by DA. Okay. But here the difference is we do not have money involved. The preference of VNF and the server both are based on the allocation cost. Simulation. We conduct simulations with this setup. We consider different SFC specification like the number of VNFs in the service chain, the location requirement of each VNF, the latency constraint of the service chain. Okay. We also consider different resource capacities and different resource costs. and we consider 4 types of VMs. And here is our topology. We have 5 areas and also 5 edge service providers. We consider 2 alternatives for comparison. The first is capacitated house allocation, or CHA. It's a one-sided preference matching protocol. In our application, we assume that ESPs has preferences on network services, while network services do not have preferences over ESPs. So network service providers choose edge systems at random. The other is random. Here, network services were randomly assigned to edge system with bit price set to the mediate. Here is the result about average profit. For the network service provider, the profit decreases as the number of network services increases. The proposed approach has the highest profit. For edge system providers, the average profit slightly increases as the number of network services increases. Here, the proposed approach has a lower profit compared with CHA. The result of the number of served network services. Okay. Here, the proposed approach also has the highest number of served network services. We also studied the impact of bit increments delta on performance. We can see that as delta increases, the number of iterations in bargaining decreases. This is reasonable because with small delta value, a network service provider can have many chances to send an offer to the same edge system, each time with a small increment on the bit price. But this is no longer true with large delta value. And this also explains the result of the number of served network services. As delta increases, the number of served network services decreases because network service providers has fewer chances to send offers to the same edge system. For every profit of NSP, large delta value also means lower profit. This is because large delta value also means lower granularity of bit price. On the other hand, large delta value will give edge system higher profit. Conclusion: we have proposed the decentralized framework for network service provider to negotiate with edge service providers possible SFC deployments with associated payments. The negotiation involves a check for possible placement of each VNF in the SFC to MEC in the ESP. This is also done by a matching protocol. And the proposed approach are profitable for both sides. When compared with counterparts, the proposed approach slightly favors network service providers, and it makes the most average number of network service deployed. Thank you.